Remembering the Past with LSTM. In the preceding sections, we explored deep neural networks, DNNs, and their versatile applications in time series forecasting, particularly in multi-step and multi-output configurations. DNNs excel at learning complex, nonlinear relationships within data. However, their fundamental architecture, which processes each input independently, presents inherent limitations when dealing with sequential data where the order of observations is crucial. This is where recurrent neural networks, RNNs, and, more specifically, long short-term memory, LSTM, networks emerge as powerful alternatives. The challenge of sequential data. Consider a time series, such as daily stock prices or hourly temperature readings. The value at any given time point is not independent. It is heavily influenced by previous values. For instance, tomorrow's stock price depends heavily on today's closing price, and a sudden drop today might signal a trend that continues tomorrow. If we were to randomly shuffle the order of these observations, the data would lose its meaning for forecasting purposes. The same applies to natural language. The sentence "dog bites man" has a distinctly different meaning from "man bites dog," purely due to the order of words. Standard DNNs, despite their depth and capacity for learning, inherently treat each input as a separate, isolated instance. When a DNN processes a sequence, say code snippet, it takes code snippet as an input vector and outputs a prediction. It does not possess an internal mechanism to remember or carry information about code snippet as it processes code snippet. Each layer's output is purely a function of its current input, not a cumulative understanding of a sequence. This lack of an internal state or memory makes them ill-suited for tasks where understanding the context and dependencies across a sequence is paramount. While we can use techniques like sliding windows to feed segments of a sequence to a DNN, this approach provides a fixed, limited historical context and doesn't allow the network to dynamically learn and adapt its memory over arbitrary sequence lengths. Introducing recurrent neural networks, RNNs. To address the limitations of standard feed-forward networks in handling sequential data, recurrent neural networks, RNNs, were developed. The defining characteristic of an RNN is its recurrent connection or loop, which allows information to persist from one step of the sequence to the next. Conceptually, an RNN has an internal memory or hidden state that is updated at each time step. This hidden state captures information about the sequence process so far and is then passed along to the next step. Imagine an RNN processing a sentence word by word. As it processes the then cat, then sat, it maintains a hidden state that gradually builds an understanding of the sentence's meaning. When it encounters Matt, it uses not only the word Matt itself, but also the accumulated cont, ext from the cat sat, to make a more informed prediction or understanding. This ability to maintain and update an internal state is what allows RNNs to model temporal dependencies. However, basic RNNs suffer from a significant practical problem, the vanishing gradient problem. During training, gradients, which indicate how much parameters should change, can become extremely small as they are propagated backward through many time steps. This makes it difficult for the network to learn long-term dependencies, relationships between events that are far apart in a sequence. For example, if a critical piece of information appears at the beginning of a very long time series, a simple RNN might forget it by the time it reaches the end. The power of long short-term memory, LSTM, networks. Long short-term memory, LSTM, networks were specifically designed to overcome the vanishing gradient problem inherent in traditional RNNs, enabling them to effectively learn and remember long-term dependencies. The long short-term memory name itself highlights its core capability. It can remember information for extended periods, long-term, while also being able to selectively forget or update information at any given moment, short-term. Think of an LSTM network as having a sophisticated memory cell that runs through the entire sequence. This memory cell is not just a simple hidden state. It's protected and regulated by special mechanisms called gates. These gates act like intelligent filters controlling the flow of information into and out of the memory cell. Forget gate decides what information from the previous memory cell state should be discarded. This allows the network to forget irrelevant past information. Input gate decides which new information from the current input and previous hidden state should be stored in the memory cell. Output gate decides what part of the memory cell's current state should be output as the new hidden state. These gates, typically implemented using sigmoid neural network layers, allow the LSTM to selectively retain or discard information, making it incredibly effective at capturing complex patterns and dependencies over long sequences. This is why LSTMs are particularly well suited for time series forecasting. They can remember critical past events or trends that occurred many time steps ago, allowing for more accurate predictions of future values. In the context of time series forecasting, LSTMs can learn to recognize patterns that span across days, weeks, or even months of data, making them invaluable for tasks like predicting stock market movements, energy consumption, or weather patterns, where the future is often influenced by events far in the past. We will delve deeper into the specific architecture and implementation of these powerful networks in the subsequent sections, exploring how these gates function in detail and how to leverage them using Keras for various forecasting tasks. Exploring the recurrent neural network, RNN. In the preceding chapters, we explored linear models and deep neural networks, DNNs, that primarily process independent data points. However, many real-world datasets possess an inherent temporal or sequential structure. Consider financial time series, where the current stock price is heavily influenced by past prices and trading volumes, or natural language, where the meaning of a word depends on the words that precede it. For such data, models that can remember and leverage past information are essential. This is where recurrent neural networks, RNNs, come into play. What is a recurrent neural network, RNN? A recurrent neural network is a type of neural network specifically designed to handle sequential data. Unlike traditional feed-forward networks where information flows in one direction from input to output, RNNs have loops that allow information to persist. This internal memory, often referred to as a hidden state, enables the network to make predictions based on not just the current input, but also on the entire sequence of previous inputs. Think of it like a human processing a sentence. When you read the word apple, your understanding of that word might change if the previous word was red versus Macintosh. Your brain inherently carries context from previous words to interpret the current one. RNNs aim to mimic this contextual understanding. Practical applications of RNNs. Time series forecasting, predicting future stock prices, energy consumption, weather patterns, or sales figures based on historical data. Natural language processing, NLP. Text generation, creating coherent sentences or paragraphs. Machine translation, translating text from one language to another. Sentiment analysis, determining the emotional tone of a piece of text. Speech recognition, converting spoken language into text. Video analysis, understanding actions in video sequences. The architecture of a basic RNN. At its core, a basic RNN cell processes an input at a given time step and produces an output, while also updating an internal hidden state that is passed to the next time step. This hidden state is the memory of the network. Imagine an RNN processing a sequence of inputs, $x1, x2, $xt. At each time step $t$1, it receives the current input $xt. 2, it receives the hidden state from the previous time step, $ht. For the very first step, $t equals $0. $h0 is typically initialized to zeros. 3, it combines $xt and $ht, $1, to compute a new hidden state, $ht. 4, it uses $ht to compute an output, $yt. This process repeats for every element in the sequence. Unrolling the RNN. While RNNs are often depicted compactly with a loop, it's more intuitive to visualize them unrolled over time. This unrolled view clarifies how information flows from one time step to the next. Consider a simple RNN cell. At each time step $t, The hidden state $HT$ is calculated using a nonlinear activation foo. Function, like code snippet or code snippet, applied to a combination of the current input $XT$ and the previous hidden state $H$. The output $YT$ is then derived from the current hidden state $HT$. The equations for a basic RNN cell are $HT equals \text 10 WHH HT 1 plus WXH XT plus BH where $XT$ input at time step $T$, $HT$, hidden state at time step $T$, $YT$ output at time step $T$, $WHH weight matrix for the recurrent connection hidden to hidden, $WXH weight matrix for the input to hidden connection, $W weight matrix for the hidden to output connection, $BH dollar by dollar bias vectors. Notice that the same weight matrices $WHH $WXH $W and biases $BH dollar by dollar are used across all time steps. This sharing of parameters is a crucial aspect of RNNs, allowing them to learn sequential patterns and generalize across different positions in a sequence. It's what makes the recurrent aspect work. The hidden state, RNN's memory, in action. The hidden state $HT$ is the memory of the RNN. It encapsulates information learned from all previous inputs in the sequence up to time step $T$. As the RNN processes new inputs, this hidden state is continuously updated, reflecting the evolving context. Let's walk through a conceptual example, predicting the next character in a sequence. Imagine we want our RNN to learn patterns in simple sequences like HELLO. Initial state. We start with an initial hidden state, often a vector, of zeros, representing no prior information. Download the code on one pagecode substack. Our process begins with encode snippet, which is typically a vector of zeros. This signifies that at the very beginning of processing a sequence, the network has no prior context. Processing the first character H. The RNN takes H as input, combines it with the code snippet, and computes a new hidden state. This new hidden state now remembers that H has been seen. Download the code on one pagecode substack. Here, code snippet conceptually represents the internal operations of an RNN cell. It takes the current inputs embedding and the previous hidden state, combines them, and applies a nonlinear function, code snippet in this case, to produce the new hidden state. We've also defined code snippet to simulate how characters are converted into numerical representations for the network. Processing the second character. Now, the RNN takes C as input, but critically, it also takes code snippet, the hidden state from processing H, as its previous hidden state. The new hidden state code snippet will now contain information about both H and E. Download the code on one pagecode substack. As E is processed, the code snippet function receives code snippet as its code snippet. This is the core of recurrence. The output of one step becomes an input to the next, allowing information to flow and accumulate. Processing LO. This process continues. Each new hidden state, code snippet, accumulates more information from the sequence. Download the code on one pagecode substack. By the time the network has processed, the final hidden state code snippet ideally contains a rich representation of the entire sequence hello. This memory can then be used to perform tasks like predicting the next character, e.g., if we were training it to predict W for hello world, or classifying the sequence, e.g., is this a greeting? This conceptual walkthrough illustrates how the hidden state acts as a dynamic summary of the sequence seen so far, allowing the network to build context over time. The vanishing gradient problem. While basic RNNs are powerful for sequential data, they suffer from a significant limitation known as the vanishing gradient problem. This issue severely restricts their ability to learn long-term dependencies, meaning they struggle to connect information that is separated by many time steps. What causes vanishing gradients? During the training of neural networks, parameters, weights, and biases are updated using backpropagation, which relies on calculating gradients. In RNNs, backpropagation happens through time, BP, meaning gradients are propagated backward not just through layers but also through time steps. Consider the chain rule in calculus. When you multiply many small numbers together, the product becomes extremely small. In RNNs, the gradients are repeatedly multiplied by the weight m. A trice is $W, $, across many time steps. If the values in these weight matrices are small, e.g., less than 1, then multiplying them over and over again for distant time steps causes the gradients to shrink exponentially. Intuitive analogy, the fading echo. Imagine shouting into a long, echoing tunnel. Near the entrance, your voice is loud and clear. Information from recent past inputs, like the last few words in a sentence or the last few hours of stock data, has a strong impact on the current hidden state and output. The gradients for these recent inputs are strong. Deeper in the tunnel, the echo of your voice becomes fainter and fainter until it's barely audible or completely gone. Similarly, information from inputs far in the past, like the first few words of a long document or stock data from weeks ago, has a progressively weaker influence on the current hidden state. The gradients for these distant inputs vanish, becoming too small to effectively update the network's weights. Because the gradients become so small, the network's weights associated with earlier time steps receive minimal updates. This means the RNN effectively forgets information from the distant past, making it difficult to learn dependencies that span many time steps. Impact on time series forecasting. In time series forecasting, the vanishing gradient problem means that a basic RNN might struggle to identify long-term trends. If a stock's price today is influenced by a major economic wide change that occurred months ago, a basic RNN might fail to capture this dependency because the gradient signal from that distant event has vanished. Process long sequences. For very long time series, like years of daily sensor readings, the RNN might only be able to learn patterns from the most recent data points, ignoring crucial information from earlier periods. This inability to retain long-term memory is a significant limitation for many real-world sequential data problems. The need for advanced RNN architectures. The vanishing gradient problem is a fundamental hurdle for basic RNNs. To overcome this, more sophisticated recurrent architectures have been developed. The most prominent of these are long short-term memory, LSTM, networks, and gated recurrent units, GRUs. While LSTMs are the focus of the next section, it's important to understand why they were invented. They were designed specifically to address the vanishing gradient problem by introducing a more complex internal structure that allows them to selectively remember or forget information over long periods. Brief mention of gated recurrent units, GRUs. GRUs are a simpler variant of LSTMs. They combine the forget and input gates into a single update gate and merge the cell state and hidden state. While simpler, they often achieve comparable performance to LSTMs on many tasks and are computationally less intensive. They are another successful approach to mitigating the vanishing gradient problem. Ending the limitations of basic RNNs, particularly the vanishing gradient problem and its impact on long-term memory, provides crucial context for appreciating the innovations introduced by architectures like LSTMs and GRUs. These advanced models form the backbone of many state-of-the-art solutions for sequential data processing. Examining the LSTM architecture. Long short-term memory, LSTM. Networks are a special kind of recurrent neural network, RNN, designed to overcome the limitations of traditional RNNs, particularly their struggle with remembering information over long sequences. Basic RNNs often suffer from the vanishing gradient problem, where gradients become too small during backpropagation through time, making it difficult for the network to learn long-term dependencies. LSTMs introduce a sophisticated internal mechanism that allows them to selectively remember or forget information, effectively managing their internal memory. Core components. the cell state and hidden state. At the heart of an LSTM unit are two crucial states that propagate through time. Cell state, code snippet often referred to as the memory highway or conveyor belt. The cell state is the primary channel for carrying long-term information. It runs straight through the entire chain of LSTM units, with only minor linear interactions. This direct path allows information to flow across many time steps without being significantly altered or diminished by vanishing gradients. Think of it as a persistent memory bank that can add or remove information as needed. Hidden state, code snippet. This state is the actual output of the LSTM unit at a given time step. It contains information from the current input and the previous hidden state, but its content is also influenced by the cell state. The hidden state is what's pick ally passed to the next layer or used for predictions. It represents the short-term or processed memory that is immediately relevant for the current time steps computation. The power of LSTMs comes from the way these two states are updated and controlled by specialized gates. Gating mechanisms, controlling the flow of information. Each LSTM unit features three primary gates: the forget gate, the input gate, and the output gate. These gates are neural network layers themselves, typically consisting of a sigmoid activation function. The sigmoid function squashes values between 0 and 1, allowing the gates to decide how much of each piece of information should pass through. A value close to 0 means forget entirely or let nothing through, while a value close to 1 means remember completely or let everything through. 1. The forget gate. The forget gate, code snippet, determines what information from the previous cell state, code snippet, should be discarded. This is crucial for preventing the cell state from accumulating irrelevant or outdated information. For example, in natural language processing, if a new subject is introduced in a sentence, the forget gate might decide to forget the old subject's gender or number information. The forget gate takes the current input, code snippet, and the previous hidden state, code snippet, as input. It then applies a sigmoid activation function to a linear transformation of these inputs. $ft equals \sigma wf h t x t plus bf . Here, code snippet, weight matrix for the forget gate. Code snippet, bias vector for the forget gate. Code snippet, concatenation of the previous hidden state and the current input. Code snippet, sigmoid activation function. Let's illustrate this with a conceptual Python snippet. We'll define a sigmoid function and then show the calculation. Download the code on one Pagecode Substack. The code snippet is the result of the linear transformation. Next, we apply the sigmoid function to get the final gate values. Download the code on one Pagecode Substack. Each value in code snippet will be between 0 and 1, representing the forget factor for each dimension of the cell state. A value close to 0 means forget this part, while a value close to 1 means keep this part. 2. The input gate. The input gate, code snippet, and a candidate value gate, code snippet or code snippet, work together to decide what new information should be added to the cell state. This is a two-step process. 1. Input gate, code snippet. This gate, also using a sigmoid activation, decides which values from the candidate vector should be updated. It acts as a filter, determining which parts of the new information are important enough to be considered for addition to the cell state. 2. Candidate cell state, code snippet or code snippet. This gate, typically using a tan activation function, creates a new candidate vector of values that could be added to the cell state. The tan function SCA less values between -1 and 1, providing a range of potential contributions, positive or negative. The equations are $it equals \sigma y xt plus by $. $gt égale tan wg cdot xt moins 1 o xt plus bg $. Here, code snippet, weights and biases for the input gate. Code snippet, weights and biases for the candidate's cell state gate. Code snippet, hyperbolic tangent activation function. Let's extend our Python example to calculate these. Download the code on OnePageCode Substack. The code snippet values indicate which parts of code snippet are relevant. The code snippet values are the potential new information. Updating the cell state. Once code snippet, and code snippet are computed, the new cell state, code snippet, is calculated. This is the most critical step as it directly addresses the vanishing gradient problem. The update is primarily an additive operation, which helps gradients flow more easily. The previous cell state, code snippet, is first multiplied element-wise by the forget gate, code snippet. This selectively discards old information. Then, the candidate cell state, code snippet, is multiplied element-wise by the input gate, code snippet, which scales the new information based on its perceived importance. Finally, these two results are added together to form the new cell state, code snippet. $CT equals FT backslash audit CT 1 plus it backslash audit GT $. Here, code snippet, element-wise multiplication, Hadamard product. This additive update is key to mitigate vanishing gradients. Instead of repeatedly multiplying gradients, which can lead to exponential decay, the LSTM allows gradients to flow directly through the cell state via addition. The gates merely control the magnitude of the information flow, rather than repeatedly squashing it. Let's continue the Python implementation for the cell state update. Download the code on OnePageCode Substack. This code snippet now holds the updated long-term memory, which will be passed to the next LSTM unit. 3. The output gate. Finally, the output gate, code snippet, determines what part of the new cell state, code snippet, will be output as the hidden state, code snippet. The hidden state is what the next layer of the network, or the next LSTM unit, will see. First, the output gate calculates its activation using a sigmoid function, similar to the other gates. Then, the newly computed cell state, code snippet, is passed through a tan function to scale its values between -1 and 1. This scaled cell state is then multiplied element-wise by the output gate's activation. $OT equals backslash sigma, well backslash HT plus bow $. $HT equals OT backslash audit backslash tan CT $. Here, code snippet, weights and biases for the output gate. This mechanism allows the LSTM to control not only what information is stored in the memory, cell state, but also what information is revealed to the subsequent layers or time steps, hidden state. Completing the Python example with the output gate and hidden state calculation. Download the code on OnePageCode Substack. This code snippet is the final output of the LSTM cell for the current time step and will be passed to the next time step's LSTM cell as code snippet. The full forward pass of an LSTM cell. To consolidate, here's a conceptual class representing a single LSTM cell's forward pass, demonstrating how all these components interact in sequence. Download the code on OnePageCode Substack. Now, let's instantiate and run a single forward pass of our custom LSTM cell. Download the code on OnePageCode Substack. This code demonstrates the flow of information through a single LSTM unit. In a full LSTM network, these units would be chained together, with code snippet and code snippet from one time step becoming code snippet and code snippet for the next. How LSTMs mitigate vanishing gradients. The core reason LSTMs succeed where basic RNNs fail regarding long-term dependencies lies in the additive nature of the cell state update. In a basic RNN, the hidden state is updated multiplicatively at each step, code snippet. When back-propagating through many time steps, the gradients are multiplied by the Jacobian of this transformation at each step. If the eigenvalues of these Jacobians are consistently small, due to the code snippet derivative being small over large ranges or small weights, the gradients shrink exponentially, leading to the vanishing gradient problem. The network effectively forgets information from early time steps because the gradients carrying that information become negligible. LSTMs, however, update their cell state via the equation code snippet. Notice the code snippet sign. This additive update creates a shortcut for gradients. If the forget gate code snippet is close to 1, the gradient can flow almost unimpeded through the code snippet pathway to earlier time steps. This constant error carousel, CEC, allows the cell state to retain information over long periods because gradients don't necessarily vanish. The gate's code snippet and code snippet merely scale the information being passed or added, rather than causing a complete multiplicative collapse of the gradient. This enables LSTMs to learn dependencies spanning hundreds or even thousands of time steps, making them highly effective for sequential data like time series or natural language. Practical implications and applications. The ability of LSTMs to selectively remember and forget information makes them indispensable for time series forecasting, where understanding long-term trends and patterns is critical. For instance, in predicting stock prices, an LSTM might learn to remember the overall market sentiment or economic indicators from many days ago, while forgetting day-to-day noise that is no longer relevant. Time series forecasting. LSTMs can capture complex temporal dependencies, such as seasonality, trends, and cyclical patterns in financial data, energy consumption, or weather. Natural language processing. NLP tasks like machine translation, sentiment analysis, and text generation heavily rely on LSTMs to understand context and dependencies across long sentences or documents. For example, in a sentence like "the man who was wearing a blue hat was walking his dog," an LSTM can maintain the man as the subject even with intervening clauses, ensuring correct pronoun resolution later. Speech recognition. LSTMs are used to process audio sequences, where the meaning of a sound often depends on previous sounds or words. By understanding the intricate dance between the cell state and the three gates, one can appreciate how LSTMs effectively manage memory in a neural network, unlocking their power for complex sequential data analysis. The forget gate. The long short-term memory, LSTM, network introduces a sophisticated mechanism to selectively retain or discard information over time, effectively addressing the short-term memory, limitation, and vanishing gradient problem inherent in traditional recurrent neural networks, RNNs. At the heart of this mechanism are specialized gates that control the flow of information. The first gate we will examine is the forget gate. The primary purpose of the forget gate is to decide which information from the past cell state, code snippet, should be thrown away or forgotten, and which should be retained. This is crucial for managing the long-term dependencies within sequential data. Imagine analyzing stock market trends. A temporary, non-recurring anomaly from months ago might be irrelevant for predicting tomorrow's price, while fundamental economic indicators from years past might still hold significant predictive power. The forget gate dynamically determines this relevance. Inputs to the gate. The forget gate makes its decision based on two key pieces of information. 1. The previous hidden state, code snippet. This represents a summary of the network's understanding of the sequence up to the previous time step. 2. The current input, code snippet. This is the new data point at the current time step. These two inputs are combined, typically by concatenation, before being fed into a neural network layer within the gate. Concatenation means joining the two vectors, end-to-end, to form a single, longer vector. This combined vector provides the gate with a comprehensive view of both the immediate new information and the distilled context from the past. The sigmoid activation function in action. The output of the forget gate is generated by applying a sigmoid activation function to the result of a linear transformation of the combined inputs. The sigmoid function squashes its input into a range between 0 and 1. An output close to 0 indicates that the corresponding piece of information from the previous cell state should be completely forgotten. An output close to 1 indicates that the information should be fully retained. Values between 0 and 1 allow for partial forgetting or partial retention. This continuous, probabilistic output allows the network to learn a nuanced decision about information flow, rather than a simple binary keep or discard. Mathematical formulation. Let's look at the precise mathematical formulation of the forget gate. $ft equals \sigma wf \ht. on XT plus BF $. Here's a breakdown of each component. Code snippet. The forget gates activation vector at the current time step code snippet. Each element in this vector will be a value between 0 and 1. Code snippet. The sigmoid activation function. Code snippet. The weight matrix for the forget gate. This matrix is a learnable parameter of the LSTM model. During training, the network adjusts the values in code snippet to optimize its forgetting decisions. COD. E-snippet. The concatenated vector of the previous hidden state, code snippet, and the current input, code snippet. Code snippet. The bias vector for the forget gate. This is also a learnable parameter that allows the gate to shift its activation threshold. Code snippet represents matrix multiplication, or dot product. The linear transformation, code snippet, maps the combined input into a space that the sigmoid function then transforms into the final forget gate output. The role of pointwise multiplication. The output of the forget gate, code snippet, directly interacts with the previous cell state, code snippet, through pointwise multiplication, also known as Hadamard product. This operation multiplies corresponding elements of two vectors or matrices. The result of this pointwise multiplication is a filtered version of the previous cell state, where values corresponding to a code snippet close to 0 are effectively zeroed out, forgotten, and values corresponding to code snippet close to 1 are passed through unchanged, retained. Consider a small numerical example. Suppose a single element of our previous cell state code snippet is code snippet, and the corresponding element of the forget gate output code snippet is code snippet. The result of the pointwise multiplication for this element would be code snippet. This drastically reduces the value, effectively forgetting much of that information. Now, if code snippet was code snippet for the same code snippet element, the result would be code snippet. This value is largely retained, indicating that this piece of information is still considered important. This selective element-wise scaling is how the forget gate precisely controls the information flow from the past into the current cell state calculation. Mitigating the vanishing gradient problem. The forget gate's mechanism plays a critical role in addressing the vanishing gradient problem. In traditional RNNs, gradients can shrink exponentially as they are backpropagated through many time steps, making it difficult for the network to learn long-term dependencies. The LSTM's cell state, code snippet, acts as a conveyor belt of information. Because information flows through the cell state with minimal transformations, primarily pointwise multiplication by the forget gate's output, gradients can propagate much more easily across long sequences. The forget gate decides how much of the previous information to keep, rather than forcing it through a series of nonlinear activations at every step. By selectively allowing information to pass through this relatively linear path, the forget gate helps maintain the magnitude of gradients, enabling the network to learn and remember dependencies that span hundreds or even thousands of time steps. Conceptual code walkthrough, number PY. Let's illustrate the operations within the forget gate using conceptual Python and number PY. We'll use dummy tensor shapes and values to mimic the data flow. First, let's define our dummy inputs, the previous hidden state and the current input. Download the code on one patch code Substack. In this initial step, we set up code snippet and code snippet as number PY arrays. Code snippet encapsulates the memory from the past, while code snippet is the new information arriving at the current time step. The code snippet is set to 1 for simplicity, meaning we're looking at a single example's processing. Next, we concatenate these two inputs. This combined vector will be fed into the linear transformation. Download the code on one patch code Substack. Concatenation joins the two vectors along the last axis, creating a wider vector that provides all the necessary information for the gate to make its decision. The resulting dimension is code snippet. Now, we define the learnable parameters, the weight matrix, code snippet, and the bias vector, code snippet. The output dimension of the forget gate and all other gates is typically the same as the hidden dimension of the LSTM cell, as it will interact with the cell state. Download the code on one patch code Substack. The code snippet matrix is shaped to perform a linear transformation from the concatenated input dimension to the code snippet, which is the dimension of the cell state and hidden state. The code snippet bias vector is added to this transformation. Weights are initialized small to prevent large initial activations. With our parameters defined, we can perform the linear transformation and apply the sigmoid activation function to get the forget gates output. Download the code on one patch code Substack. The code snippet function performs the matrix multiplication. The code snippet function then converts these raw values into probabilities between 0 and 1. Each value in code snippet now represents how much of the corresponding information from the previous cell state should be kept. Finally, we demonstrate the pointwise multiplication with a dummy previous cell state, code snippet. Download the code on one patch code Substack. This final step clearly shows how the code snippet acts as a filter on code snippet. Values in code snippet close to 0 will cause the corresponding elements in code snippet to become very small, effectively discarding that information. Conversely, values close to 1 will preserve the information. This code snippet will then be combined with newly proposed information from other gates to form the final code snippet. Practical implications and real-world scenarios. In practical time series forecasting, the forget gate is invaluable. Consider predicting stock prices. Forgetting a sudden, temporary market anomaly, e.g., a flash crash due to a technical glitch, might be relevant for a few hours, but should be largely forgotten after the market corrects. Keeping this extreme, non-representative data point as strong long-term memory could skew future predictions. The forget gate learns to assign a low forget factor to such transient events. Retaining fundamental economic indicators, e.g., interest rate changes, GDP growth, or long-term historical trading patterns, e.g., seasonal trends, remain highly relevant over extended periods. The forget gate learns to assign a high forget factor to these persistent signals, ensuring they are carried forward in the cell state. Similarly, in weather forecasting, a single erroneous sensor reading from days ago should be forgotten, while general climate patterns or the persistence of a large-scale weather system should be retained. The learnable weights and biases of the forget gate allow the LSTM to dynamically adapt its memory retention strategy based on the specific patterns and noise present in the training data. Abstraction in deep learning frameworks. While understanding these internal mechanics is crucial for grasping how LSTMs work, deep learning frameworks like Keras or TensorFlow abstract away much of this complexity. When you use a code snippet layer, all these internal computations, concatenation, matrix multiplications, bias additions, and sigmoid activation for the gates are handled automatically. You define the input shape and the desired output, hidden, dimension, and the framework manages the creation and optimization of code snippet, and all other necessary weights and biases during training. However, knowing the underlying operations empowers you to debug, optimize, and choose the right models for your specific time series challenge. 1.5.2.2 The input gate. The forget gate, as discussed, determines what information to discard from the previous cell state. Complementary to this, the input gate is responsible for deciding what new information from the current input and the previous hidden state should be stored in the cell state. It's the mechanism through which an LSTM selectively incorporates new, relevant data into its long-term memory. Conceptually, the input gate operates in two primary stages. 1. Deciding what to update. A sigmoid layer, often referred to as the input gate layer, determines which values to update. It outputs values between 0 and 1, where 1 indicates completely update and 0 indicates don't update. 2. Creating new candidate values. A hyperbolic tangent, tan, layer, often called the candidate value layer, generates a vector of new candidate values that could potentially be added to the cell state. These values are scaled between -1 and 1. These two outputs are then combined to form the information that will be added to the cell state. Inputs to the input gate. Similar to the forget gate, the input gate takes two primary inputs, The current input data at time step code snippet, denoted as code snippet. The hidden state from the previous time step code snippet, denoted as code snippet. These two inputs are typically concatenated into a single vector code snippet before being fed into the gate's internal layers. This concatenation allows the gate to consider both the most recent NT output of the network and the current data point when making decisions about new information. The sigmoid layer, deciding what to update code snippet. The first component of the input gate is a sigmoid function. This function takes the concatenated code snippet and code snippet, applies a linear transformation, multiplication by a weight matrix code snippet, and addition of a bias vector code snippet, and then passes the result through a sigmoid activation. The output of this sigmoid layer, denoted as code snippet, is a vector where each element is between 0 and 1. These values represent the importance or relevance of each corresponding new candidate value. A value close to 1 indicates that the network deems the associated candidate value highly important and worthy of being added to the cell state, while a value close to 0 suggests it's less relevant. Mathematically, this operation is expressed as $it equals \sigma y \nxt plus by $. Here, code snippet is the input gate output vector. $\sigma$ is the sigmoid activation function. Code snippet is the weight matrix for the input gate layer. Code snippet is the bias vector for the input gate layer. Code snippet is the concatenation of the previous hidden state and the current input. The TAN layer, creating new candidate values, code snippet. The second component of the input gate is a TAN function. This layer also takes the same concatenated code snippet and code snippet as input, but it uses a different set of weights, code snippet, and biases, code snippet, for its linear transformation before applying the TAN activation. The output of this TAN layer, denoted as code snippet, often called the candidate cell state, or new memory content, is a vector of values ranging from -1 to 1. These values represent the potential new information that could be added to the cell state. The TAN function is used here because its output range of -1 to 1 helps to regulate the values, preventing them from growing too large and destabilizing the network, while still allowing for both positive and negative contributions to the cell state. Mathematically, this operation is expressed as $GT equals \tan WG \HNXT plus BG $. Here, code snippet is the candidate cell state vector. $\tan$ is the hyperbolic tangent activation function. Code snippet is the weight matrix for the candidate value layer. Code snippet is the bias vector for the candidate value layer. Role of weights and biases. It's critical to understand that code snippet, and code snippet are learnable parameters. During the training process, the neural network adjusts these weights and biases through backpropagation to optimize its performance. These parameters dictate how the network transforms the input data and previous hidden state to make decisions about what new information is relevant and how it should be scaled. Each gate within the LSTM, forget input, output, has its own distinct set of weights and biases, allowing for specialized processing. Step-by-step numerical walkthrough of the input gate. Let's illustrate the operations of the input gate with a simplified numerical example using Python and NumPy. We'll assume very small vector dimensions for clarity. First, we'll set up our mock inputs and parameters. Download the code on OnePageCode Substack. Here, we've defined the necessary activation functions and initialized our hypothetical previous hidden state, code snippet, and current input, code snippet. We also set up dummy weight matrices, code snippet, and bias vectors, code snippet, for both the input gate sigmoid layer and its TAN layer. The dimensions are chosen to be small, but representative of the operations. Next, we concatenate the hidden state and current input. This combined vector will be the actual input to both internal layers of the input gate. Download the code on OnePageCode Substack. The code snippet is now a single vector that represents all the information the input gate has available to make its decision. Now, let's calculate the output of the sigmoid layer, code snippet, which determines what new information is relevant. Download the code on one pagecode Substack. The code snippet vector, with values between 0 and 1, tells us how much we should consider adding each corresponding part of the new candidate information. For instance, if code snippet has a component of code snippet, it means 90% of the corresponding candidate value is deemed relevant. Following this, we calculate the output of the tan layer, code snippet, which generates the actual candidate values. Download the code on one pagecode Substack. The code snippet vector contains the scaled candidate values, ranging from -1 to 1. These are the raw, new memories that the network is proposing to add to the cell state. Finally, the input gate combines these two outputs by performing a pointwise multiplication. This step effectively scales the candidate values, code snippet, by their respective importance scores, code snippet. Download the code on one pagecode Substack. The code snippet vector is the final output of the input gate's internal processing. This vector represents the specific, filtered, and scaled new information that the LSTM wants to inject into its long-term memory. Contribution to cell state update. The input gate's output, code snippet, represents the new information to be added to the cell state. This new information is then combined with the filtered old information from the previous cell state, which was determined by the forget gate, code snippet. The complete formula for updating the cell state code snippet at time code snippet is a crucial combination of both the forget gate's decision and the input gate's decision. $CT equals CT 1 \FT plus at \GT $. Here, code snippet is the updated cell state at the current time step. Code snippet is the cell state from the previous time step. Code snippet is the output of the forget gate, values between 0 and 1, determining what to keep from code snippet. Code snippet is the output of the input gate's sigmoid layer, determining what new information to update. Code snippet is the output of the input gate's tan layer, the candidate new values. Let's continue our numerical example to show how code snippet is updated. Download the code on one pagecode Substack. This final step clearly demonstrates how the forget gate dictates what to forget from the past, and the input gate dictates what new information to remember. The cell state effectively becomes a blend of selectively retained old memories and newly incorporated insights. Practical application analogy. Stock market analysis. Consider an LSTM being used for stock price prediction. Code snippet could be the current day's trading volume, news sentiment, or a sudden price spike. Code snippet could represent the model's understanding of recent market trends or investor behavior. The input gate would process code snippet and code snippet. If code snippet indicates an unusually high trading volume accompanied by positive news, interpreted through code snippet, the input gate's code snippet might output values close to 1, signifying that this new information is highly relevant. Simultaneously, code snippet would generate scaled values representing the magnitude and direction of this new information, e.g., a strong positive signal. For future price movement, the resulting code snippet would then be a strong positive contribution to this cell state, effectively embedding this critical new event into the network's long-term memory. This allows the LSTM to adjust its future predictions based on significant new developments, rather than just relying on past patterns. High-level code perspective, abstraction, and deep learning frameworks. While understanding these internal mechanics is crucial for deep expertise, modern deep learning frameworks like TensorFlow and Keras abstract much of this complexity. When you define and code snippet layer, all the intricate operations of the forget, input, and output gates, along with the cell state update, are handled internally. For example, creating an LSTM layer in Keras looks deceptively simple. Download the code on one pagecode Substack. The code snippet layer internally manages the code snippet, code snippet, code snippet, code snippet, and similar for other gates. Parameters, performs the concatenations, matrix multiplications, bias additions, and applies the sigmoid and tan activations, just as we've detailed. The code snippet parameter directly corresponds to the dimensionality of the hidden state, code snippet, and the cell state, code snippet. This abstraction allows practitioners to focus on model architecture and data preparation, while the framework efficiently executes the complex underlying computations. 5.2.3 The output gate. The journey through the LSTM cell's internal mechanisms culminates with the output gate. While the forget gate decided what information to discard and the input gate determined what new information to store, the output gate's crucial role is to control what information from the updated cell state will be exposed as the hidden state for the current time step. The hidden state code snippet is not only passed to the next LSTM cell, but also serves as the primary output of the current cell, often used for predictions or further processing in the network. Purpose and function. The output gate acts as a filter, selectively extracting relevant information from the long-term memory, cell state code snippet, to form the short-term memory, hidden state code snippet. It ensures that only necessary and useful information is propagated forward, preventing the hidden state from becoming overwhelmed with irrelevant details while still leveraging the rich context stored in the cell state. Think of the cell state code snippet as a vast library containing all the information accumulated over time. The output gate is like a librarian who, given a specific query, the current input and previous hidden state, decides which specific books, parts of the cell state, are relevant to summarize and present as the answer for the current moment. Inputs and internal operations. To make its decision, the output gate considers two primary pieces of information. 1. The previous. Hidden state code snippet provides context from the immediate past. 2. The current input code snippet, the new data point being processed. These two inputs are combined and passed through a sigmoid activation function to generate a filter value. This filter then interacts with the transformed cell state to produce the new hidden state. Let's break down the mathematical operations. Step 1. Calculate the output gate's activation code snippet. First, the output gate determines which parts of the cell state are relevant. It does this by taking a linear combination of the previous hidden state code snippet and the current input code snippet, and then squashing the result with a sigmoid function. OT equals \sigma, with \xt plus UO \ht 1 plus bo. Where code snippet, the output gate's activation vector at time step code snippet. Its values range from 0 to 1, indicating how much of each component of the cell state should be outputted. Code snippet, the current input vector. Code snippet, the hidden state from the previous time step. Code snippet, weight matrices for the input code snippet and previous hidden state code snippet, respectively. These are learned parameters during training. Code snippet, bias vector, also a learned parameter. $\sigma$. The sigmoid activation function, which maps values to a range between 0 and 1. This function is crucial because it allows the gate to act as a soft switch, deciding how much information to let through. 0 for complete blockage, 1 for full pass-through, and values in between for partial pass-through. Step 2. Transform the current cell state code snippet. Before being filtered, the current cell state code snippet is passed through a hyperbolic tangent code snippet activation function. $\tilde CT equals \text 10 CT. Where $CT. The cell state code snippet transformed by the code snippet function. Code snippet, the hyperbolic tangent function, which maps values to a range between -1 and 1. Why code snippet on the cell state? The code snippet function scales the values of the cell state to a range of -1 to 1. This normalization is important because it ensures that the contributions from the cell state to the hidden state remain within a bounded range. If the cell state values were unbounded, their direct multiplication with the output gate's sigmoid values, 0 to 1, could lead to very large or very small hidden state values, potentially causing instability in the network, e.g., exploding or vanishing gradients, or making the hidden state less representative of the core information. By squashing code snippet to -1 to 1, code snippet helps in creating a well-behaved hidden state. Step 3. Compute the new hidden state code snippet. Finally, the new hidden state code snippet is computed by performing a pointwise multiplication of the output gate's activation, code snippet, and the code snippet transformed cell state, code snippet. $. Hate odotte. Exten CT. Where? Code snippet. The new hidden state at time step code snippet. $\oda$ denotes pointwise multiplication, also known as Hadamard product. This operation multiplies corresponding elements of two vectors or matrices of the same dimension. For example, if $A equals a 1, if $2 and $B equal B1, B2, then $A\oda B equals a 1\B1, a 2\B2. In the context of LSTMs, this means each element of the code snippet vector is scaled by the corresponding element of the code snippet vector. The result, code snippet, is the information that the LSTM cell decides to output at the current time step. It represents a filtered version of a long-term memory, code snippet, incorporating insights from the current input and previous hidden state. This code snippet is then passed to the next LSTM cell in the sequence and can also be used as input for a subsequent layer, e.g., a dense layer for classification or regression. The significance of the hidden state code snippet. The hidden state code snippet is arguably the most important output of an LSTM cell at any given time step. It serves two critical purposes. 1. Context for the next time step. It provides a condensed summary of past relevant information to the subsequent LSTM cell in the sequence, allowing the network to maintain a coherent understanding of the sequential data. 2. Input for prediction/output layer. For tasks like time series forecasting or natural language processing, code snippet is often fed into a dense layer or another network component to make a final prediction or generate an output for the current time step. For instance, in a sentiment analysis task, the final code snippet of the sentence might be used to classify the overall sentiment. The output gate's ability to selectively expose information from the cell state is what makes LSTMs so effective at handling long-term dependencies. It prevents irrelevant information from diluting the hidden state, ensuring that code snippet remains a focused and meaningful representation of the current context. Practical example. Predicting the next stock price. Consider a scenario where you're using an LSTM to predict the next day's stock price based on historical data, e.g., daily open, high, low, close prices, volume. Code snippet, cell state contains the long-term memory of the stock's performance trends, market sentiment indicators, and overall economic context accumulated over many days. Code snippet, current input, today's stock price data, news, and perhaps a sudden market event. Code snippet, previous hidden state, yesterday's summary of the market, including its immediate reaction to previous events. The output gate will use code snippet and code snippet to decide which aspects of the comprehensive code snippet are most relevant for today's prediction. For example, if there was a major news announcement today, code snippet, the output gate might allow more emphasis on code snippet components related to market volatility or sector-specific trends, while downplaying less relevant historical patterns. The resulting code snippet would then be a concise summary of the most pertinent information from the past and present, which is then fed to a final prediction layer to estimate tomorrow's price. Code illustration, numerical walkthrough of the output gate. Let's simulate the operations of an output gate with numerical examples using number py. We'll assume simple two-dimensional vectors for clarity, but in real LSTMs, these would be much larger. First, we'll set up our learned weight matrices and bias vectors, along with our input data. Download the code on one Pagecode Substack. In this initial setup, we define the dimensions of our vectors and matrices. Code snippet represents the size of our hidden state and cell state, while code snippet is the size of our current input. We then create sample numerical values for the previous hidden state, code snippet, current input, code snippet, and the current cell state, code snippet. These values would typically come from the previous time step calculations or the input data. Finally, we initialize the weight matrices, code snippet, and bias vector, code snippet, for the output gate, which are the parameters that the LSTM learns during training. Next, we implement the activation functions, sigmoid and tan. Download the code on one patch code substack. Here, we define the code snippet and code snippet functions. The code snippet function is crucial for the gates, as it outputs values between 0 and 1, effectively acting as a soft switch to determine how much information to let through. The code snippet function, on the other hand, squashes values between -1 and 1, which is useful for normalizing the cell state before it contributes to the hidden state. Now, we calculate the output gates activation, code snippet. Download the code on one patch code substack. This segment computes the first part of the output gates operation. It performs a linear transformation on the current input, code snippet, and the previous hidden state, code snippet, using their respective weight matrices, code snippet, and adds the bias, code snippet. The result is then passed through the code snippet function to produce code snippet, a vector where each element indicates the openness of the output gate for that specific dimension of the cell state. Finally, we transform the cell state and compute the new hidden state. Download the code on one patch code substack. In this crucial step, the current cell state, code snippet, is passed through the code snippet function to scale its values between -1 and 1. This code snippet vector represents the candidate information from the long-term memory that could potentially be exposed. Then, the code snippet vector, our filter, is multiplied element-wise with code snippet. The result, code snippet, is the new hidden state. This code snippet vector encapsulates the information from the cell state that the output gate deemed relevant to output at the current time step, providing a concise summary for the next cell and for any subsequent prediction layers. Common pitfalls and best practices. Understanding gate interactions. A common pitfall is to view each gate in isolation. It's crucial to remember that the forget, input, and output gates work in concert. The output gate's decision is only meaningful if the cell state, code snippet, itself has been properly updated by the forget and input gates. Gradient flow. The code snippet activation on the cell state helps in preventing exploding or vanishing gradients within the cell state itself, as it keeps values bounded. However, issues can still arise across many time steps, which is why LSTMs are not a complete panacea for vanishing gradients, but they significantly mitigate the problem compared to vanilla RNNs. Hyperparameter tuning. The dimensionality of the hidden state and cell state, often the same size, is a critical hyperparameter. A larger dimension allows the LSTM to store more complex information, but increases computational cost and the risk of overfitting. Initialization. Proper initialization of weights and biases, e.g., using Xavier or He initialization, is vital for stable training of LSTMs, just as it is for other neural networks. Regularization. Techniques like dropout are often applied to the hidden state or inputs to prevent overfitting in LSTMs, especially when dealing with smaller datasets or complex models. 15.3 Implementing the LSTM architecture. Having thoroughly explored the conceptual underpinnings of the long short-term memory, LSTM, architecture, including the intricate workings of its forget, input, and output gates, we now transition to the practical realm of implementing these powerful models. This section lays the essential groundwork by preparing our time series data, which is the foundational step for any machine learning project, especially for deep learning models like LSTMs. Our focus will be on setting up the data for various time series forecasting tasks, single-step, multi-step, and multi-output predictions. Throughout this implementation, we will leverage previously developed utility functions and classes, specifically the code snippet class, introduced in Chapter 13, for creating appropriate time series windows, and the code snippet function from Chapter 14 for streamlining the model training process. Preparing the time series data. The first and most crucial step in any time series forecasting project is to load and appropriately structure your data. For this chapter, we will continue using the interstate traffic dataset, a real-world dataset containing hourly traffic volume, temperature, and other relevant features. This dataset is ideal for demonstrating how LSTMs can learn complex temporal patterns to predict future values. For robust model development and evaluation, it is a standard and critical practice to divide your dataset into distinct train, ING, validation, and test sets. This separation is particularly vital in time series forecasting to prevent data leakage and ensure that the model's performance is genuinely reflective of its ability to generalize to unseen future data. Training set, used to train the model, allowing it to learn patterns and relationships within the data. Validation set, used during the training process to tune hyperparameters and perform early stopping. It provides an unbiased evaluation of a model's fit on the training dataset while tuning the model's hyperparameters. Test set, a completely unseen dataset, reserved for the final evaluation of the model's performance after all training and hyperparameter tuning are complete. This provides an unbiased estimate of the model's generalization capability. We will begin by loading these 3 datasets using the code snippet library. Download the code on one Pagecode Substack. The first step in any Data Central project is to import the necessary libraries. Here, we import code snippet and alias it as code snippet, which is a widely adopted convention. The code snippet calls are included to enhance the readability of data frame outputs in your console, ensuring that you can see all columns and a wider display of your data. Next, we load the training dataset from a CSV file. Download the code on one Pagecode Substack. Here, code snippet is used to load our training data. The code snippet argument is crucial for time series data. It instructs cod eSnippet to treat the first column of the CSV file as the data frame's index. In time series datasets, this column commonly holds timestamps or sequential identifiers, which are essential for maintaining the temporal order of observations. By setting it as the index, code snippet can perform time-based operations more efficiently. After loading the data, it's good practice to immediately inspect its structure and content to ensure it has been loaded correctly. Download the code on one Pagecode Substack. The code snippet method provides a quick glimpse of the first 5 rows of the data frame, allowing you to visually confirm column names, data types, and initial values. Code snippet offers a more comprehensive summary, including the number of entries, column names, the count of non-null values for each column, useful for identifying missing data, and the data type of each column. For time series, paying attention to the index type, e.g., code snippet if parsed correctly, and numerical feature types is important. We repeat this process for the validation dataset. Download the code on one Pagecode Substack. The validation set mirrors the structure of the training set, but contains data from a later period. Its primary role is to provide an unbiased evaluation of the model's performance during training, guiding decisions on hyperparameter tuning and when to stop training to achieve optimal generalization. Finally, we load the test dataset. Download the code on one Pagecode Substack. The test set is the ultimate arbiter of your model's real-world performance. It contains data that the model has never seen, nor has it influenced any part of the training or tuning process. This ensures that the final reported performance metrics are a true reflection of how the LSTM model will behave on new, unseen data in a production environment. Connecting to data preparation utilities, the code snippet class. With our raw data loaded into code snippet data frames, the next logical step in time series forecasting is to transform this continuous stream of data into a format suitable for supervised learning models like LSTMs. This is where the code snippet class, which we extensively developed in Chapter 13, becomes indispensable. Recap the code snippet class. The code snippet class is designed to automate the process of creating input-output pairs, or windows, from time series data. It handles windowing, defining the length of the input sequence, code snippet, and the length of the sequence to be predicted, code snippet. Shifting, specifying the offset between the end of the input window and the start of the label window, code snippet. Feature and label selection, allowing you to specify which columns from your data frame should be used as input features and which as labels to be predicted. Data splitting, internally managing the code snippet, and code snippet to generate corresponding code snippet objects for efficient training in TensorFlow. Keras, normalization/standardization. If implemented in your code snippet version, handling data scaling within each window to improve model stability and performance. The code snippet class abstracts away the complexities of sliding window creation, making it much easier to experiment with different window sizes and forecasting horizons. Placeholder for code snippet instantiation. While the full implementation of creating windows for single-step, multi-step, and multi-output LSTMs will be detailed in subsequent sections, it's important to understand conceptually how the code snippet we just loaded would be passed to the code snippet class. Download the code on one patch code Substack. This placeholder demonstrates how code snippet would be initialized with our code snippet, and code snippet. Key parameters like code snippet, and code snippet define the structure of our time series windows, while code snippet specifies what we intend to predict. The code snippet object then internally handles the creation of code snippet objects, which are optimized for feeding data into Keras models. Connecting to model training utilities, the code snippet function. Once the data is prepared by the code snippet class into suitable input-output sequences, the next phase involves defining and training our LSTM model. To streamline this process and ensure consistent training practices, we will utilize the code snippet function, WH. It was developed and detailed in Chapter 14. Recap: the code snippet function. The code snippet function is a wrapper around the standard Keras model compilation and fitting process. Its main benefits include standardized compilation, automatically compiles a Keras model with a specified optimizer, loss function, and metrics. Efficient training loop, handles the code snippet call, passing the window data from code snippet instances. Callbacks, integrates common callbacks such as code snippet to prevent overfitting by stopping training when validation loss stops improving, and code snippet to save the best model weights. Logging, provides clear output during training, showing progress and performance metrics. By using code snippet, we avoid repetitive code for model compilation and training, allowing us to focus more on the LSTM architecture itself and less on the boilerplate training setup. Placeholder for code snippet call. Similarly, we provide a conceptual placeholder for how the code snippet function would be invoked, linking the prepared data windows to the training process. Download the code on one patch code Substack. This placeholder illustrates the typical usage of code snippet. It takes our Keras model, which will be an LSTM in upcoming sections, and a code snippet instance. The code snippet and code snippet parameters control the training duration and early stopping behavior, ensuring efficient and robust model training. Summary of forecasting tasks. If the data loaded and the utility functions conceptually linked, we are now fully prepared to implement LSTMs for different forecasting challenges. Single-step forecasting, predicting the very next value in a time series, e.g., predicting traffic volume for the next hour. This involves a code snippet of one. Multi-step forecasting, predicting a sequence of future values, e.g., predicting traffic volume for the next 6 hours. This involves a code snippet greater than one. Multi-output forecasting, predicting multiple distinct features at a future time step, e.g., predicting both traffic volume and temperature for the next hour. This involves specifying multiple columns in code snippet within code snippet and an LSTM output layer designed for multiple outputs. The subsequent sections will dive into the specific LSTM architectures and their implementation details for each of these forecasting scenarios, building directly upon the data preparation steps laid out here. 1.5.3.1 Implementing an LSTM as a single-step model. Having explored the theoretical underpinnings of the long short-term memory, LSTM, architecture, it's time to transition to its practical implementation. In this section, we will build our first LSTM model using Keras, specifically designed for single-step time series forecasting. This means our model will predict the very next value in a sequence based on a historical window of data. We'll leverage the code snippet class and the code snippet utility function introduced in previous chapters to streamline our workflow. 15.3.1.1 setting up the data window for LSTM. Before we can define and train our LSTM model, we need to prepare our time series data into a format suitable for recurrent neural networks. This involves creating windows of data where each window consists of an input sequence, the past observations, and a corresponding label, the value we want to predict. The code snippet class is designed precisely for this purpose. For a single step model, our goal is to predict the immediate next value. We're using code snippet of 24, meaning the model will consider the previous 24 hours of data to make its prediction. The code snippet parameter will be set to 1, indicating that we are predicting the value at code snippet given data up to code snippet. While we are performing single-step prediction, we will set code snippet to 24. This seemingly counterintuitive choice is made specifically to facilitate the visualization end of our predictions, allowing us to plot a 24-hour window of actual values alongside our single-step predictions, effectively showing a rolling forecast over time. Let's initialize our code snippet object. Download the code on one PageCode Substack. The code snippet object, once instantiated, automatically prepares the training, validation, and test datasets. The code snippet of 24 means each input sequence will contain 24 time steps. The code snippet ensures that the label for each input sequence is the data point immediately following that sequence. The code snippet is crucial for visualization. While the model predicts only one step ahead, the code snippet provides 24 future actual values as context when plotting, making the single-step rolling forecast visually comprehensible. To confirm the data shape that our LSTM model will receive, we can inspect an example batch generated by the code snippet. Download the code on one PageCode Substack. The output will typically show input shapes like code snippet and label shapes like code snippet. For our code snippet, the input shape will be code snippet, and the label shape will be code snippet. The LSTM layer in Keras expects 3D input, code snippet. Our code snippet provides exactly this format, with code snippet corresponding to code snippet. 15.3.1.2 defining the LSTM model architecture. Now, let's define our LSTM model. We will use Keras's code snippet API to stack layers. The core of our model will be in code snippet layer, followed by a code snippet output layer. Download the code on one PageCode Substack. The code snippet layer is the workhorse here. It processes the input sequence code snippet and, due to its internal gates, forget, input, output, and cell state, can selectively retain or discard information over long sequences. This capability makes LSTMs particularly well suited for time series data, where long-term dependencies are common, and traditional dense networks or simpler recurrent neural networks, RNNs, might suffer from vanishing or exploding gradients. The code snippet layer takes the processed information from the LSTM and outputs our single predicted value. Keras's code snippet layer defaults to code snippet activation for its recurrent steps and code snippet for its gates, which are standard choices. The code snippet layer here uses a linear activation function by default, which is suitable for regression problems where the output is a continuous value. To get a clear overview of our model structure, including the output shapes of each layer and the total number of trainable parameters, we can use the code snippet method. Download the code on one PageCode Substack. The code snippet output will show that the code snippet layer, with code snippet, outputs a 3D tensor, while the code snippet layer collapses this to a 2D tensor code snippet because it implicitly takes the output of the last time step from the sequence produced by the LSTM. The parameter count reflect TS the complexity of the model, which is significantly higher than simple dense networks due to the internal mechanisms of the LSTM units. 15.3.1.3 compiling and training the LSTM model. With the model architecture defined, the next step is to compile it and then initiate the training process. The code snippet function, which we assume is defined from previous chapters, simplifies this by setting up the optimizer, e.g. atom, the loss function, e.g. mean absolute error or M, and evaluation metrics. It also typically includes callbacks for early stopping and learning rate reduction, which are crucial for efficient and stable training. Download the code on one patch code Substack. During training, the model iteratively adjusts its internal weights and biases to minimize the chosen loss function, MAE in this case, on the training data, while monitoring performance on the validation set to prevent overfitting. The code snippet object return contains a record of the training loss and metrics over each epoch. 1.5.3.1.4 Evaluating the LSTM model performance. After training, it's essential to evaluate the model's performance on unseen data to get an unbiased estimate of its generalization capabilities. We'll evaluate the model on both the validation set, which was used during training for early stopping, and the completely held-out test set. Mean absolute error, MAE, is a robust metric for regression tasks like time series forecasting, as it directly measures the average magnitude of errors, providing a straightforward interpretation. Download the code on one patch code Substack. To easily compare the performance with other models, e.g., from previous sections of the book, we can print the stored MAE values. Download the code on one patch code Substack. These MAE values provide a quantitative measure of how well our LSTM model is predicting the next hour's traffic volume. Lower MAE values indicate better performance. 1.5.3.1.5 Visualizing single-step LSTM predictions. While numerical metrics are crucial, visualizing the predictions against the actual values provides invaluable qualitative insight into the model's behavior. The code snippet method of our code snippet class is designed to take our trained model and display a few sample predictions, allowing us to visually assess accuracy and identify any systematic errors. Download the code on one patch code Substack. The generated plots will show input sequences, the actual future values for context derived from code snippet, and the model's single-step predictions. Observe how closely the predicted line follows the actual traffic volume, paying attention to peaks, troughs, and general trends. This visual inspection can often reveal nuances that a single MAE metric might miss. 1.5.3.1.6 Making individual predictions with the LSTM model. For practical applications, you'll often need to use your trained model to make predictions on new, unseen data, one sequence at a time. The code snippet method in Keras allows us to do this. Remember that an LSTM model expects a 3D input of shapecode snippet. Even for a single sequence prediction, you need to add a batch dimension. Download the code on one patch code Substack. In this example, code snippet accesses the single predicted value from the output tensor. This demonstrates how you would feed a new sequence of 24 hours of traffic data to the model and get its prediction for the 25th hour. 1.5.3.1.7 Hyperparameter tuning considerations. The choice of code snippet, 24 hours, and the number of LSTM units, 32, are critical hyperparameters. Code snippet. This determines how much past information the model considers for each prediction. A larger code snippet allows the model to capture longer-term dependencies and patterns, e.g., daily or weekly seasonality. However, it also increases computational cost and might introduce irrelevant noise if the dependencies are short-lived. The optimal code snippet often depends on the inherent periodicities in your time series data. For hourly traffic data, 24 hours is a reasonable starting point to capture daily patterns. Number of LSTM units. This relates to the model's capacity or complexity. More units allow the model to learn more intricate relationships, but also increase the risk of overfitting and computational expense. Fewer units might lead to underfitting. The optimal number is typically found through experimentation and cross-validation. These hyperparameters, along with others like learning rate, batch size, and the number of layers, are typically optimized through techniques such as grid search, random search, or more advanced methods like Bayesian optimization. For practical applications, understanding these choices is as important as the code itself. 1.5.3.2 Implementing an LSTM as a multi-step model. This section extends our practical application of long short-term memory, LSTM, networks from single-step to multi-step time series forecasting. In multi-step forecasting, the goal is to predict multiple future time steps simultaneously, rather than just the immediate next step. This approach, often referred to as direct multi-step forecasting, is powerful for scenarios where an entire future sequence is required at once, such as predicting the next 24 hours of traffic volume or energy consumption. Data preparation for multi-step forecasting. For multi-step forecasting, the configuration of our code snippet object becomes crucial. While the code snippet defines how much historical data the model observes, the code snippet now specifies the number of future time steps the model is expected to predict. The code snippet parameter is also vital. It determines the offset between the end of the input window and the beginning of the label window. For direct multi-step forecasting of the immediately following code snippet steps, code snippet will typically be equal to code snippet. Let's configure a code snippet to predict the next 24 hours of code snippet using the preceding 24 hours of data. Download the code on one patch code Substack. In this configuration, code snippet means our model will observe 24 hours of historical data. Code snippet indicates that the model is expected to produce 24 future predictions. The code snippet is CR. Usual. It ensures that the 24-hour prediction window immediately follows the 24-hour input window. This setup is the defining characteristic of a direct multi-step forecast, where the model generates a single prediction encompassing the entire future sequence. This differs from a recursive multi-step forecast, where the model predicts one step, then uses that prediction as input to forecast the next, and so on. To verify the shapes of the data batches generated by our code snippet, we can inspect a single batch from the training dataset. This helps confirm that our inputs and labels are correctly formatted for multi-step predictions. Download the code on one patch code Substack. You should observe that code snippet will be code snippet, e.g., code snippet if the default code snippet is 256 and code snippet is 1 for code snippet. Crucially, code snippet will be code snippet, e.g., code snippet, confirming that our labels are indeed sequences of 24 future time steps. This code snippet format is exactly what Keras LSTM layers expect. Multi-step LSTM model architecture. The architecture for a multi-step LSTM model is similar to its single-step counterpart, but with a critical difference in the LSTM layers configuration, the code snippet parameter. Download the code on one patch code Substack. Let's break down the key components of this architecture. Code snippet. This layer forms the core of our recurrent network. Code snippet. This specifies the number of LSTM units, or HITA, in units. More units generally allow the model to learn more complex patterns, but increase computational cost and the risk of overfitting. Code snippet. This is the crucial parameter for enabling multi-step output. When code snippet is set to code snippet, the LSTM layer outputs the hidden state for each time step in the input sequence, rather than just the hidden state of the last time step. If our input sequence has 24 time steps, the LSTM will output a sequence of 24 hidden states, each of size 32, the number of units. The output shape will be code snippet. Code snippet. Explicitly setting the input shape helps Keras build the model graph immediately. Code snippet would typically be code snippet, e.g., code snippet. Code snippet. This is a standard fully connected layer. Code snippet. This indicates that each time step in the sequence output by the LSTM will be mapped to a single predicted value. Code snippet. This initializer sets the initial weights of the dense layer to 0. While not universally required, it can sometimes be useful in time series forecasting to ensure the model starts making predictions close to 0, or to encourage the LSTM to fully learn the mapping without initial bias from the dense layer. It might also be used when the output values are expected to be centered around 0, or when we want the LSTM's initial output to dominate the predictions. To understand precisely how the data flows through this model and how code snippet impacts the output shape, it's highly beneficial to examine the model summary. Download the code on one patch code Substack. The model summary will show that the code snippet layer, with code snippet, outputs a shape like code snippet, where code snippet is the batch size, code snippet is the code snippet, which is also the output sequence length, and code snippet is the number of LSTM units. The subsequent code snippet layer then takes this code snippet input and applies its transformation to the last dimension, resulting in an output shape of code snippet. This code snippet output precisely matches the code snippet shape of our code snippet labels, making it perfectly suitable for direct multi-step forecasting. Training and evaluation. Training the multi-step LSTM model uses the same code snippet utility function introduced earlier. This function typically configures the model with an optimizer and a loss function, then trains it on the provided code snippet. For time series regression, code snippet is a common and robust choice for the loss function, as it is less sensitive to outliers than mean squared error, MSE. The code snippet optimizer is a popular default due to its efficiency and good performance across a wide range of problems. Download the code on one PageCode Substack. After training, we evaluate the model's performance on the validation and test sets. We typically use the same metric used for training, such as ME, to objectively compare against other models or baselines. Download the code on one PageCode Substack. By explicitly printing the ME directly after evaluation, we get immediate feedback on the model's performance on unseen data. A lower ME indicates a more accurate forecast. Visualizing multi-step predictions. Visualizing the multi-step predictions is crucial for qualitatively assessing the model's performance and understanding its strengths and weaknesses. The code snippet method can be used to display sample input sequences, their true future values, and the model's multi-step predictions. Download the code on one PageCode Substack. When interpreting these plots, observe how well the predicted sequence aligns with the true sequence over the entire 24-hour forecast horizon. You might notice that while the initial parts of the prediction might be accurate, errors tend to accumulate over longer forecast horizons. This is a common and inherent challenge in multi-step forecasting because the model has to predict further into the future without new actual data, relying solely on its learned patterns from the initial input. Challenges and considerations in multi-step forecasting. Multi-step forecasting, while powerful, presents unique challenges compared to single-step forecasting. 1. Error accumulation. As observed in the visualizations, errors made in predicting earlier time steps within the forecast horizon can compound, leading to increasingly less accurate predictions further into the future. This is a fundamental limitation, even FO, are direct multi-step models, as the single prediction must capture the entire future sequence's dynamics. 2. Increased complexity. The model needs to learn more complex, long-range dependencies to accurately predict an entire sequence. This can require more extensive training data, larger model capacities, e.g., more LSTM units, or more sophisticated architectures. 3. Hyperparameter tuning. The choice of hyperparameters, such as code snippet, and a number of LSTM units, e.g., 32 in our example, significantly impacts model performance. Tuning these is often an iterative process. For instance, a larger code snippet allows the model to see more history, potentially capturing longer-term dependencies, but also increases model complexity and computational cost. The number of LSTM units determines the model's capacity to learn intricate patterns. Too few may underfit, too many may overfit. Despite these challenges, LSTMs are well suited for multi-step forecasting due to their ability to learn and retain long-term dependencies within sequential data. They are widely used in critical applications requiring future sequence predictions, including energy consumption forecasting, predicting hourly energy demand for the next 24 to 48 hours to optimize grid operations and resource allocation. Financial market prediction, forecasting stock prices or market indices for the next few days to inform trading strategies. Weather forecasting, predicting temperature, humidity, or precipitation for the coming hours or days, which is vital for agriculture, disaster preparedness, and daily life. Traffic management, predicting traffic flow patterns for the next several hours to anticipate congestion and manage transportation networks effectively. This direct multi-step approach is one of several strategies. Other methods include recursive multi-step forecasting, where single-step predictions are generated iteratively, with each prediction being fed back as input for the next, or multi-output models, where each output neuron predicts a different future time step, often without requiring code snippet from the LSTM. The choice of strategy depends on the specific problem, data characteristics, and desired trade-offs between model complexity, computational efficiency, and prediction accuracy. 15.3.3 Implementing an LSTM as a multi-output model. In the realm of time series forecasting, it's often necessary to predict more than one variable simultaneously. For instance, you might want to forecast both future traffic volume and temperature, as these variables can be correlated and influence each other. This is known as multi-output or multivariate time series forecasting. Building upon our single-step and multi-step LSTM implementations, this section guides you through configuring an LSTM model to predict multiple target variables at once. Configuring the data window for multiple outputs. The code snippet utility class, which we've established in previous sections, is highly flexible and can be adapted for multi-output scenarios by specifying the target columns. Instead of a single code snippet, we now provide a list of code snippet. For this multi-output example, we will focus on a single-step prediction horizon, meaning we predict the next single time steps values for both traffic volume and temperature based on a sequence of past observations. Download the code on OnePageCode Substack. In the code above, code snippet is configured to create input sequences of 24 hours, code snippet, and corresponding labels that are the values of code snippet and code snippet for the single hour immediately following the input sequence, code snippet, code snippet. This setup is crucial for our single-step, multi-output prediction. The code snippet parameter now accepts a lease T, allowing the code snippet to extract multiple target variables for each prediction. Designing the multi-output LSTM architecture. The core of a multi-output LSTM model lies in its final code snippet layer. Instead of having a single unit for a univariate prediction, this layer will have as many units as there are target variables. In our case, since we are predicting both code snippet and code snippet, the code snippet layer will have 2 units. A common point of confusion arises with the code snippet parameter of the code snippet layer. When code snippet, the LSTM layer outputs a sequence of hidden states, one for each time step in the input sequence. This is typically used when stacking multiple LSTM layers or when applying a code snippet layer to process each output in the sequence. However, when a code snippet layer directly follows in code snippet layer with code snippet without a code snippet wrapper, Keras implicitly takes the output of the last time step from the LSTM's output sequence and feeds it into the code snippet layer. This effectively means that although the LSTM processes the entire input sequence and produces a sequence of outputs, only the final output of that sequence is used by the subsequent code snippet layer for the prediction. For a single-step prediction, this behavior is often desired, as we are interested in the final forecast based on the entire input sequence. Download the code on OnePageCode Substack. Here, code snippet creates an LSTM layer with 32 memory cells. Code snippet is specified to ensure that the LSTM outputs a sequence of 32-dimensional vectors, one for each input time step. This is a common practice even if only the last output is eventually used, as it can sometimes lead to better internal representations during training compared to code snippet, which only outputs the last hidden state. The code snippet layer then takes the final 32-dimensional vector from the LSTM's output sequence and transforms it into our 2-dimensional prediction, temperature and traffic volume. To understand the flow of data and the output shapes at each layer, it's invaluable to inspect the model summary. Download the code on OnePageCode Substack. The code snippet output is critical for debugging and understanding your network. You'll observe that the output shape of the code snippet layer will be code snippet, batch size, time steps, units, because code snippet. However, The code snippet layer following it will show an input shape corresponding to code snippet. This confirms that the code snippet layer implicitly only processes the last time steps output from the LSTM when code snippet is used without a code snippet wrapper. Training the multi-output LSTM model. Training a multi-output model is similar to training a single output model, leveraging our code snippet utility function. The key difference is that the model's output will now have multiple dimensions, which the loss function must be able to handle. For regression tasks like hours, code snippet, MAE, or code snippet, MSE, are suitable as they can naturally compute the error across all output dimensions. It's important to note that if your target variables have vastly different scales, e.g., temperature in tens versus traffic volume in thousands, the model might prioritize learning the variable with a larger scale. In such cases, normalizing your target variables, e.g., scaling them to a 0 to 1 range, before training can significantly improve performance and ensure the model gives appropriate attention to all outputs. Download the code on one patch code Substack. The code snippet function handles the specifics of setting up the optimizer, like atom, and the loss function, like NA, which are inherently compatible with multidimensional outputs. The training process then proceeds as usual, minimizing the chosen loss across both predicted outputs. Evaluating multi-output model performance. After training, evaluating the model's performance on unseen validation and test sets is crucial. For multi-output models, evaluation metrics like ME will typically represent the average error across all outputs. If you need to assess performance for each output individually, you would typically need to perform manual predictions and calculate metrics for each target column separately. Download the code on one patch code Substack. The code snippet method computes the overall loss and metrics for the multi-output model. The output code snippet reflects the aggregated ME across both code snippet and code snippet predictions. This provides a single, concise measure of the model's general accuracy. Making and interpreting multi-output predictions. Visualizing the predictions is perhaps the most intuitive way to understand how well our multi-output model performs. The code snippet method is designed to handle multiple code snippet and will plot each predicted output alongside its actual values. To understand the raw predictions, we can also use code snippet on a batch of data. Download the code on one patch code Substack. The code snippet array will have a shape like code snippet, where code snippet is 2 in our case. You can then index this array to access the predictions for each specific target variable, e.g., code snippet for temperature and code snippet for traffic volume. Finally, visualizing the results provides a clear picture of the model's performance. Download the code on one patch code Substack. The code snippet method will generate a plot showing both the predicted and actual values for code snippet and code snippet over a sample period, allowing for a direct visual comparison of the model's accuracy across both target variables. This visualization helps in identifying if the model is performing better for one output than the other, or if there are specific periods where predictions for either variable deviate significantly. Practical applications and challenges in multi-output forecasting. Multi-output time SC. RISE forecasting is highly applicable in various real-world scenarios beyond just traffic and temperature. Consider industrial monitoring, predicting multiple sensor readings, e.g., temperature, pressure, vibration, from a machine to anticipate different types of failures. Financial markets, forecasting different components of a financial portfolio, such as the prices of several correlated stocks or commodities. Environmental science, predicting various air quality metrics, e.g., PM 2.5, O3, and O2 simultaneously at a given location. Energy management, predicting electricity demand alongside renewable energy generation, solar, wind, for grid balancing. Despite its power, multi-output forecasting comes with its own set of challenges. Differing scales. As mentioned, if target variables have vastly different ranges, it can bias the model towards minimizing error on the larger scale variable. Normalization of target variables is a common and effective mitigation strategy. Inter-output correlations. While LSTMs can implicitly learn correlations, understanding and leveraging explicit correlations between outputs can sometimes improve model performance, potentially through more complex network architectures or loss functions. Loss function selection. While MAE and MSE are a general, specific applications might benefit from custom loss functions that weigh errors differently for each output, especially if one output is more critical than others. Data availability requiring ignored historical data for multiple variables can sometimes be a constraint, especially when integrating data from disparate sources. By mastering multi-output LSTM implementation, you gain a powerful tool for tackling complex, multivariate time series prediction problems, providing a more holistic and integrated view of future trends. This section consolidates our understanding of recurrent neural networks, RNNs, and, more specifically, long short-term memory, LSTM, networks. We will revisit their fundamental architecture, the challenges basic RNNs face, and how LSTMs ingeniously overcome these limitations through their unique gating mechanisms and cell state. Recurrent neural networks, RNNs processing sequential data. At their core, recurrent neural networks, RNNs, are specifically designed to process sequential data, where the order of information is crucial. Unlike traditional feed-forward neural networks that treat each input independently, RNNs maintain an internal memory that allows them to consider previous inputs when processing the current one. This memory is encapsulated in a code snippet, also sometimes called a code snippet, which is passed from one step in the sequence to the next. For example, in time series forecasting, the hidden state at time code snippet incorporates information from all data points up to code snippet, enabling the model to learn temporal dependencies. This makes RNNs exceptionally well suited for tasks such as time series prediction, natural language processing, and speech recognition. The recurrent connection allows the network to apply the same operation at each time step, making it efficient for variable length sequences. The vanishing gradient problem in basic RNNs. While conceptually powerful, basic RNNs suffer from a significant limitation known as the vanishing gradient problem. During the training process, specifically during backpropagation through time, BPT, the gradients used to update the network's weights can become extremely small as they propagate backward through many time steps. This occurs because the gradients are repeatedly multiplied by small values, often derived from activation functions. When gradients vanish, the network struggles to learn long-term dependencies. Information from earlier time steps either gets diluted or completely forgotten by the time it reaches later steps. This limits the model's ability to capture patterns that span long sequences, leading to a form of short-term memory, where the network primarily focuses on recent inputs. For instance, in a very long time series, an RNN might fail to connect a pattern observed hundreds of steps ago with the current prediction. Conversely, the less common exploding gradient problem can occur where gradients become excessively large, leading to unstable training. While exploding gradients can often be mitigated with techniques like gradient clipping, vanishing gradients are more insidious and require architectural solutions like LSTMs. Long short-term memory, LSTM, networks, overcoming short-term memory. Long short-term memory, LSTM, networks are a special type of RNN specifically designed to address the vanishing gradient problem and effectively learn long-term dependencies. The key innovation in LSTMs is the introduction of a cell state and AS, series of gating mechanisms that regulate the flow of information into and out of this cell state. This intricate design allows LSTMs to selectively remember or forget information over extended periods, making them highly effective for complex sequential data. The cell state, the long-term memory conduit. The code snippet, is the central component of an LSTM. It acts as a conveyor belt, running straight through the entire chain of recurrent units, carrying information across long sequences without significant degradation. This unique property is often referred to as the constant error carousel, CEC, because it implies that the error signal can flow backward through time without vanishing, allowing the network to maintain long-term memory. Unlike the code snippet, which is constantly being updated and influenced by immediate inputs, the cell state is designed to allow information to pass through relatively unchanged unless explicitly modified by the gates. This direct, uninterrupted path for information and gradients is what primarily enables LSTMs to learn long-term dependencies. Gating mechanisms, regulating information flow. LSTMs employ three primary gates, each controlled by a sigmoid neural network layer and a pointwise multiplication operation. The code snippet function, code snippet, outputs values between 0 and 1, acting as a gate controller. A 0 means let nothing through, while a 1 means let everything through. These gates determine what information is allowed to enter, exit, or remain within the cell state. 1. Forget gate code snippet. Purpose. The forget gate decides what information from the previous cell state, code snippet, should be thrown away or kept. This is crucial for managing the long-term memory, allowing the network to clear irrelevant past information. Mechanism. It takes the previous hidden state, code snippet, and the current input, code snippet, concatenates them, and passes them through a sigmoid layer. Function. The output is a vector of values between 0 and 1. A value close to 0 indicates forget this information, while a value close to 1 indicates keep this information. This gate is essential for preventing irrelevant information from accumulating in the cell state and for allowing the network to selectively reset its memory. For example, when a new topic begins in a sentence or a significant shift occurs in a time series trend. 2. Input gate, code snippet. Purpose. The input gate decides which new information from the current input, code snippet, and previous hidden state, code snippet, should be stored in the cell state. This allows the LSTM to selectively add new, relevant information to its long-term memory. Mechanism. It consists of two parts. A sigmoid layer, code snippet, that decides which values to update, i.e., which parts of the code snippet are important. A code snippet layer, code snippet, often called the code snippet or code snippet. The T creates a vector of new candidate values that could be added to the cell state. The code snippet activation function squashes values to between -1 and 1, allowing for both positive and negative contributions to the cell state. Function. The outputs of these two parts are multiplied element-wise, code snippet. This filtered candidate information is then added to the cell state, effectively updating the long-term memory with new, relevant data. 3. Output gate, code snippet. Purpose. The output gate decides what part of the current cell state, code snippet, should be output as the new hidden state, code snippet. The hidden state is then used for predictions and passed to the next LSTM unit. Mechanism. It takes the previous hidden state, code snippet, and the current input, code snippet, passes them through a sigmoid layer. The code snippet activation function is then applied to the new cell state, code snippet, to scale its values to between -1 and 1. Function. The output of the sigmoid layer is multiplied element-wise by the code snippet-activated new cell state, code snippet. This allows the LSTM to output only the relevant parts of its internal memory to the next time step and to the final prediction layer, without exposing the entire cell state. This controlled output helps in focusing the network's attention on pertinent information for the current prediction. How LSTMs address the vanishing gradient problem. The core mechanism by which LSTMs mitigate the vanishing gradient problem lies in the cell state and the forget gate. By allowing information to flow directly through the cell state via the constant error carousel, CEC, LSTMs provide a direct, relatively unobstructed path for gradients to propagate backward without vanishing. The forget gate explicitly controls this flow, allowing the network to preserve information for extended periods when its gate value is close to 1, meaning remember this, or forget it when close to 0, meaning discard this. This selective memory update, combined with the ability to add new information via the input gate, ensures that gradients related to long-term dependencies can remain strong and contribute effectively to weight updates during training. This architectural design directly enables LSTMs to capture and learn from dependencies that span hundreds or even thousands of time steps, a feat basic RNNs cannot achieve. The gates act as sophisticated filters, ensuring that only relevant information persists in the cell state, thus preventing the gradient signal from decaying over long sequences. In essence, LSTMs provide a sophisticated control mechanism over their internal memory, enabling them to learn which information to store, which to discard, and which to pass on to future steps, making them exceptionally effective for complex sequential data tasks like time series forecasting.